Yes, good evening. I welcome you all to the problem solving session of the NPTEL course on thermodynamics. Today I will solve some the assignments problem for the week 7 and then go on to some flow problems like this. So this is a general steady flow energy equation when you have a control volume, like when you have a control volume like this and there is some mass coming in and mass going out, and you consider this as a control volume. This will have an internal energy called as EV, and this mass coming in is say dm mass inlet, and this is m2, and this will have an enthalpy represented by h1, and it will be coming in at a velocity v1, and the potential energy head is represented by z1, and so on. So similarly you can have the parameters at as outlet as well, and there is some heat that is transferred in represented by q, and there is some work that is transferred out represented by wx. So on the left we have the steady state energy flow equation for this control volume. So this will be used in the upcoming problems. Now the first question, we have to match the pairs. For adiabatic throttling, we know there is no heat transfer or work transfer, but the enthalpy coming in is equal to the enthalpy out of the throttle device. So that is option B is right. And in case of turbine and rotary compressors, there is some work done on the system, and that will be equivalent to the change in enthalpy coming in and out of the system. So that is equal to this. And in case of nozzles and diffusers, there is no external work done, but there will be some change in kinetic energy as at the expense of the enthalpy energy. So this is matching with this. And in case of heat exchangers, there are multiple fluids coming in and going out of the heat exchangers at different enthalpy levels, and so this heat exchanger can be represented by the equation A. So looking at that, we will have 1B, 2D, 3C. So this is right, and 4A. The next problem, in the next question, the first law of thermodynamics for flow processes, also known as steady flow energy equation, is valid for which of the following types of fluid? So this is valid for all the type of fluid. So it is valid for inviscid, viscous, compressible and incompressible fluids. Next question, which of the following is true? In an unsteady flow process, the fluid characteristics like velocity, pressure or density at a spatial location change with respect to time. If it is not changing, it is steady flow. And option B is the characteristics like density, velocity changes from one spatial location to another but not change with the passage of time. So B, or the second, is for non-uniform or non-uniform steady flow. But for steady flow, the option 1 is right, so A is correct. In the next question, we have compressed air at 1 megapascal at 100 degrees Celsius flows through a pipe, and evacuated rigid tank of 1 meter cube volume is connected to the pipe through a valve as shown in the figure. So now the valve is open to fill the tank, and the valve closes automatically when the pressure in the tank reaches 1 megapascal. Assuming ideal case behavior, the final air temperature in the tank is dash degree Celsius. Assume process to be adiabatic. So it is told that there is no heat transfer, that is adiabatic. You can consider the rigid tank is insulated, and in this process there is no work transfer as well. We can write the steady flow energy equation, like the change in internal energy, or we'll write du is equal to enthalpy m1 h1, that is the fluid coming in, and minus m2 h2, that is fluid leaving out, and we have heat transfer into the system minus work transfer by the system. So in this case there is only one mass coming in, and there is no mass going out, and since it is adiabatic, W is 0, and we know there is no work transfer, so W is also 0, and this is du or delta U is U2 minus U1. This is equal to M1 H1. We know it is an evacuated rigid tank, so U1 is 0, so we are left with only U2, that is, so at the final state the mass of the control volume, that is this rigid tank, is same as the mass that is coming in, so that is M1 into U1 is equal to M1 into H1. Now M can get cancelled, and we are left with U equal to H, that is Cv into temperature of the air is equal to Cp into T1. Now T1 is known as 100 degrees Celsius, and Cp Cv values is also given. So we have Ta is equal to Cp is 1005 as given in the problem, and Cv is 718 into Ti is 100 degrees Celsius, so that is 373 Kelvin. So we can calculate the final temperature, air temperature in the tank. So this is 522.1 Kelvin, and it is 249.1 degrees Celsius. So this is 249.1. So do you have any questions?
No, sir.
So next problem, steam at 3 bar and 150 degrees Celsius enters the nozzle of a steam turbine with negligible velocity. The steam expands adiabatically through the nozzle and leaves at 1 bar with dryness fraction of 0.95. The exit velocity of steam is dash meter per second. So it is a nozzle. So in nozzle we know the enthalpy is converted to velocity or kinetic energy. Now we know for nozzle delta H is equal to V2 square by V1 square by 2. Now we can calculate the initial and final enthalpy. It is given at 3 bar and 150 degrees Celsius. We can use the steam table to find that. Three bar is 0.3 megapascal. So at 0.3 megapascal the saturation temperature is 133.5 degrees Celsius, whereas in the given condition it is 150 degrees Celsius. So it is a superheated steam. So we can go to the superheated steam table. So we have 0.3 megapascal or 3 bar and 150 degrees Celsius. 150 and this one. So enthalpy is 2761.2. kilojoule per kg, and enthalpy 2 is it has some dryness fraction. That means it is a mixture of water and steam. Then we have enthalpy of the fluid at second state plus dryness fraction into HFG2, and this is at 1 bar. So we need to go to the steam table. 1 bar is 0.1 megapascal, so we have it here, 0.1 megapascal, and the HF is 417.5 plus X is 0.95 into HFG is 2257.4. So we have 2562.03 kilojoule per kg. Now to calculate the velocity, it is told that the initial velocity is 0. That means the steam entering the nozzle is almost stationary with a negligible velocity. So V1 is 0. So finally we are left with V2 is equal to 2 into delta H within root. So this 2 into the change in enthalpy, that is H2 minus H1 H1 minus H2. Now we have 2 into 2761.2 minus 2562.03 into 10 power 3. So because we had kilojoule per kg, to convert to SI units we have to multiply by 10 power 3. So this is 631.14 meter per second. Now we need to find the total exit area for mass flow rate of 5 kg per second. So to find the total flow rate, we have m dot is equal to rho into A into velocity. Now we know the velocity at second state, area is unknown, and rho can be found out using the specific volume from the steam table. Now we can look into this steam table and find these are the specific volume for the water and vapor state. So here we know this volume of water is almost negligible, so we can have only this one, volume of the steam, it is 1.694. So this is V2 is X into Vg2, that is 0.95 into 1.694. So this is 1.6093 meter cube per kg. And now we have m dot as 5 kg, and so this is equal to a velocity, I would write this v as capital, v2 by specific volume v at second state. Now area can be found out into v2 is 631.14 divided by specific volume is 1.6093, which means a is 5 into 1.6093 divided by 631.14. This is 0.01275 meter square. So in the next problem we have an experimental setup where air needs to be heated steadily by a 10 kilowatt electric resistance heater flowing through an insulated duct as shown in the figure. If the air enters at 25 degrees Celsius at a rate of 2 kg per second, the exit temperature of the air is dash Kelvin. We can assume air is an ideal gas, neglect changes in potential and kinetic energy, assume Cp of air, Cv of air to be constant, and the values is also given. Now we know Q is from the steady flow equation, neglecting the other terms, you will have Q as delta H. So that is Q is equal to mCp delta T, and Q is given as 10 kilowatt, that is 10 into 10 power 3 is equal to m as mass flow rate is 2 into Cp is given as 1005 joule per kg Kelvin into delta T is T final minus T initial. So T initial is 25 degrees Celsius. So 25 degrees Celsius is 298 Kelvin. So this is Tf minus 298. Now we can find Tf as 10 into 10 power 3 divided by 2 into 1005 plus 298. This is 302.975 Kelvin. So rounding off to the nearest integer, we will have 303. Next problem. An ideal gas with constant Cp and Cv at 30 degrees Celsius and 6 atmosphere is throttled by a valve to 1 atmosphere. If the process is adiabatic and the change in kinetic energy and potential energy are negligible, the exit temperature of the gas will be dash degrees Celsius. So we have an ideal gas throttled from 6 atmosphere to 1 atmosphere, and the inlet temperature is 30 degrees Celsius. So now we can write the steady flow energy equation. So now we have change in internal energy is equal to Q minus W plus enthalpy of the mass coming in, that is MIHI minus enthalpy of the mass leaving out, so MOHO. So now for a throttle device, the change in internal energy is 0 because it is occurring at a steady state, and there is no heat transfer, there is no work transfer. We are left with only the enthalpies of the mass coming in and out. At steady state, both the mass should be same, so we will have enthalpy at h I is equal to h naught. And if the process is adiabatic, and we can assume we can neglect the kinetic energy and potential energy, so neglecting those only we have written the equation. And since it is ideal, we can assume it as an ideal gas. This is left with only Cp of Ti minus is equal to Cp of T naught. Now Cp can be constant, is constant for both the cases. So now T inlet is equal to T outlet. So at outlet we have 30 degrees Celsius, same as the inlet temperature. So in this kind of in a general throttling device, we cannot in real gas there will be something called Joule-Thomson effect. So if you reduce the pressure, in ideal gas the temperature is constant if you move from rightward to left, but in case of real gas, the temperature will increase to some region and then start decreasing. So, and this will occur at different enthalpies, enthalpy H1, H2, and you can join this line, and this is called Joule-Thomson effect. And in case of refrigeration, this throttling effect where the temperature decreases, so this portion of the where the temperature decreases when pressure is decreased, that region is used in the refrigeration cycles. And otherwise this will lead to increase in entropy, which reduces the available work and so on. The next problem: in a shower, cold water at 6 degrees Celsius flowing at a rate of 6 kg per minute is mixed with hot water at 60 degrees Celsius flowing at a rate of 6.6 kg per minute. The exit temperature of the water from the shower after the system has attained steady state is -Kelvin. Assume the specific heat of water to be constant and the changes in kinetic and potential energy to be negligible. So in this case we will have two streams. So at stream 1 we have 6 degrees Celsius and 6 kg per minute, and so this is stream 1, stream 2, and outlet is stream 3. So at stream 2 we have 60 degrees Celsius and 6.6 kilogram per minute, and at outlet we will have say T3 and m.3, and this m.3 is summation of m.1 plus m.2. In this case, if you take this as a control volume, we have m1 h1 plus m2 h2 is equal to m3 h3, and so this is from the steady flow energy equation, neglecting the other terms which are negligible, and based on law of conservation of mass, we have m1 plus m2 is equal to m3. So m3 can be found out as 6 kg per minute plus 6.6 kg per minute, so this is 12.6 kilogram per minute. Now writing the steady flow energy equation, we have this as m1 is 6 kg per minute into Cp into T1. So now again we will have m1 cpt1 plus m2 cpt2 is equal to m3 cpt3. So all the cp's will get cancelled, and so we will be left with m1 t1 plus m2 t2 is equal to m3 t3. So now t3 is equal to m1 t1 plus m2 t2 divided by m3, that is m1 plus m2. So this is 6 into 6 degrees Celsius, so we have to convert this to in Kelvin scale. It is 279 Kelvin, and for 60 it is 333 Kelvin. So this is 6 into 279 plus 6.6 into 333 divided by 12.6. So this is 307.3 Kelvin. Or the next question, we have a thermal power plant. A boiler in the thermal power plant has a volumetric capacity of say 10 meter cube and contains water in the liquid state and vapor phases at 20 bar. Initially the liquid phase occupies half the total volume. Fluid may be allowed to escape from the boiler by two valves, one at the top of the boiler and other at the bottom of the boiler. Heat is transferred to the boiler such a rate that the temperature of the fluids remain constant. Assume that no liquid particles are held in suspension in the vapor. And the first question is the amount of heat which must be transferred if 300 kg of fluid is allowed to escape slowly via the upper valve while the lower valve remains closed. So this the total volume of the boiler is 10 meter cube. And the pressure maintained is as 20 bar or 2 megapascal. So since they say both steam and water are present, it will be in the vapor dome with equilibrium between the steam and water. And in the first problem, some fluid is allowed to escape from the top valve, that is upper valve. So that it means steam is released, and this amount of steam that it is released is 300 kg, and then heat is supplied such that the temperature remains the same. So that means if the temperature has to remain same, in the vapor dome, this is TS diagram. So the temperature is remains same. So initially it may be at this state, and after some time it can go somewhere between towards the left or right. By maintaining the same temperature, that is same pressure. So because it is within the vapor phase dome, it will be at same pressure.
Sir,
Yes.
I have a doubt here.
Yeah.
Actually, because of that only I have made the mistake in assignment. Now there is one sentence, and because of that, while solving, I am getting confused.
Okay.
Assume that no particles are held in suspension in the vapor.
Yes, yes.
Okay.
Mm-hmm.
That means what I assumed, steam is a separate entity and water is a separate entity.
Yes.
Rather than there is no existence of wet steam as such.
Yes.
Okay.
Mm-hmm.
So what I have done, all the calculations means internal energy calculation.
Mm-hmm.
Actually, I made the mistake there. Means what I am supposed to think. Is while calculating internal energy,
Mm-hmm.
initial internal energy as well as final. Because
Mm-hmm.
of that sentence, what I have done,
Mm-hmm.
I have taken for water, mass of water I have calculated,
Mm-hmm.
and I have multiplied it by UF only. Okay, that
Mm-hmm.
is internal energy of liquid.
Mm-hmm.
And here I have calculated steam mass and
Mm-hmm.
multiplied by UZ,
Mm-hmm.
that is vapor, because of that sentence only. But the
Mm-hmm.
thing is, in the solution, they have calculated dryness fraction.
Mm-hmm.
Now, my question is here, if this sentence is there,
Mm-hmm.
w- there is no necessity of calculated dryness fraction. And because of that, I gone wrong. So actually, I'm having means most of the time on Wednesday I'm having some external work. That's why I'm not joining the classes
Oh, okay, okay.
today. Purposefully, I have joined only because of this question,
Mm-hmm.
because I have unable to understand why they have taken dryness fraction. Because as this sentence is clearly mentioned, there is no wet as far as wet stream existence.
Okay.
So the dryness fraction should not come in the picture. What according to me.
Mm-hmm. Yeah, yeah.
And in the solution, they have
So,
given dryness
hmm,
fraction.
so when 300 kg of the steam is taken out and that enthalpy has to be calculated, it should be say m into h, and that is hg. This is what you are mentioning, right? So this is
Yes.
300 into the enthalpy at this state, 20 bar and gas state.
Yeah. No, no, no. For enthalpy, they have done right.
Mm-hmm.
300 into Hg they have taken. No problem.
Yeah.
But while calculating internal energy in the solution, dryness
Mm-hmm.
fraction they have calculated, it is coming very less, point not one वगैरह वगैरह आता है.
Mm-hmm.
Okay. But what I think
Mm.
that also we should not consider because of that particular sentence.
Yeah, because now 300 kg of steam is taken out. Now the earlier it was 5 meter cube, and now and here 5 meter cube. After steam is taken out, it will become, I think, 6 point some meter cube. I say 5.5 meter cube.
Sir, you can solve the
Yeah,
question
yeah. Then we will see.
automatically. You
Yeah,
come to know later. Huh?
yeah.
At
Okay,
that
fine.
point, I will ask the question.
Yeah. So initially we can find from the steam table at 20 bar HF HG UF UG VF VG. So we had 20 bar, so that is 2 megapascal, and we have 906.1 as 908.5 is the enthalpy of the liquid state. I think 908.5, and this is 2798.3. UF is 906.1. This is 2599.1. This is 0.001177, and this is 0.09959 into cube per kg, and all these are kilojoule per kg. So initially it was mentioned 5 meter cube of this and 5 meter cube of steam and 5 meter cube of water is present. So we can find M as M fluid 1 plus M steam 1, and so that is M is volume, actual volume by the this specific one. So this will be meter cube in the numerator and then meter cube per kg in the denominator, then finally we will get kg. And similarly Vg1 by Vg, so this is 5 meter cube divided by Vf is 0.001177 plus 5 by 0.09959. So this is M. It is also better to calculate the MF and MG separately. So this is 5 by 0.001177, that is 4248 kilogram, and Mg1 is 5 by 0.09959, that is 50.2 kilogram. So total M is, so this is mass 1, it is 4248 plus 50.2, that is 4298.2.
Yes, यहाँ तक सब कुछ ठीक है.
Yeah. Now we can find the internal energy. So when we take the steam out, we can write the steady flow equation. So we have change in internal energy is equal to Q plus mass coming in, because since there is no mass coming in, we will directly write mass going out into enthalpy of out. So only this thing we have, some energy is added, and we have to calculate the change in internal energy. Now, so this is M1, and find in the, so this is U2 minus U1. So now for U1 is M1 into U1, or we can also write MF1 into UF1 plus MG1 plus into UG1. So that is MF1 is 4248 kg into U1 internal energy of the fluid at state 1 is 906.1 into 906.1 plus Mg1 is 50.2 into Ug1 is 2599.1. So this is internal energy at the state 1. So this is 3979 587 kilojoules. So this can be written as 3979 megajoules. Similarly, at state 2, the
Hello, sir.
Yeah.
Can I interrupt you?
Yeah, no problem.
अभी यहाँ से ही गलती हुई है. मैंने ऐसे ही कैलकुलेट किया, मेरा और आपका आंसर सेम आ रहा है.
Sorry, I don't understand Hindi. Can you talk in English, please? Yeah.
Okay, my answer and your answer is coming same now.
Yeah, okay.
But the thing is, in the solution, they have calculated dryness fraction, and they have used the formula U1 is equal to UF plus X UZ minus UZ minus UF.
UG minus UF. Yeah, I think this should also give the same answer.
No.
Okay, let's see. So UF is 906.1 plus dryness fraction we have to find. So dryness fraction is M steam by total M. mg by mf plus mg. This is 50.2 divided by total mass is 4298.2. So this is 0.01168.
68.
Yeah. Now this is at state 1. So this will have, then we will have into 0.01168 into Ug is 2599.1 minus 906.1. This comes to be 925.874 kilojoule per kg, and total internal energy is m1u1, that is total kg is 4298.2 into 925.874. So I'm getting 3979.591.62 kilojoules. So this is 3979 megajoules. Yeah, so this is also 3979 megajoules, right?
Yeah.
But in solution it is a different value.
So in solution, actually they have taken specific internal energy. That's why we are not able to match the answer.
Specific, okay, but finally we need only total internal energy, no? Because
Total, we want total internal
because
energy.
the mass is also changing, we need to account that. Okay. So
Yeah.
now I can find the internal energy at state 2, no? Yeah. So now we are we know that the total mass is reduced by 300 kg, that is m2 is m1 minus 300. So this is 4298.2 minus 300. That is 3998 kg. Now we know the total volume is also 10 meter cube. Now we know m2 is equal to mg2 plus mf2. This is I would write Vg2 by specific volume at second state, or it is same, and similarly this should be 10 minus Vg2 because the total volume is 10. You can write like this. Now this is Vf and this is 3998.2. Vg2 is unknown. Vg is known, that is Vg is 0.09959 plus 10 minus Vg2 divided by 0.001177. If you solve, we will get Vg2 as okay, we can try to solve here. Now 1 by 0.09959 is, this is 10.041 Vg2 plus 849.62 into 10 minus Vg2 is equal to 3998.2. So now we have 10.041 Vg2 plus 8496.2 minus 849.62 Vg2 is equal to 3998.2. Now Vg2 is 8496.2 minus 3998.2 divided by 849.62 minus 10.041. So I get 5.36 meter cube. Now Vf2 will be 10 minus 5.36, that is 4.64 meter cube. Yeah. Now internal energy at state 2, to calculate that we need mg2 and mf2. mg2 is Vg2 divided by specific volume of G, that is 5.36 divided by Vg is 0.09959. So this is 53.8 kilogram. And similarly mf2 is Vf2 by specific volume of the fluid, that is 4.64 divided by 0.001177. That is 3942.2 kilogram. Yeah. Now internal energy at state 2 is mf2 into internal energy of specific internal energy of the fluid plus mg2 ug. This is mf2 is 3942.2 into internal energy of the fluid is 906.1 plus mg2 is 53.8 into ug is 2599.1. 2599.1. So internal jet state 2 can be calculated. That is 3585967 kilojoules. So this is 3586 megajoules. I think you had a different number. 3711.
Or
Oh,
what is the problem? Actually, there are no options also. Only in rectangle we need to feed the figure.
yeah.
So
I think this is not.
Sir, how I have solved, I will tell you. Actually,
No,
I
no,
have
this
not
is
done
yeah.
because I have not followed your method here. What I have done,
No, as long as, no, I think my number was wrong. If the numbers are right, then it's fine. So it is 3711 megajoules. You are, that is right, right?
No, no, no. I have solved little differently.
Hmm.
See, initially there is means before escaping 300 kg of steam. Case 1 I am talking about, upper wall. Okay. Initially mass of water is 4248 and mass of steam is 50.20. Correct?
Yeah.
Now we have allowed 300 kg mass to go out. So what is going to happen? Out of total mass, first there is a steam is only 50, so 50 will go. And remaining water, as we are inputting the heat to the system, water is converted continuously in steam. So what I have done, now after letting out 300 kg inside, what I have assumed, there is only existence of water which is remaining inside it. No steam now. 50 kg steam is already there, which has escaped out, and remaining 250 kg is converted from water into steam. So now, when we shut the valve after 300 kg is escaping out, there is existence of only water. So what I have done for final calculation of final internal energy, I have taken remaining mass that is coming as 3998.28. Okay. Where we are matching our answers, but that I have multiplied with internal energy of only water.
Only water, yeah. But
only water,
yeah.
Because only water remains there, na?
No, we cannot tell like that because they have given the temperature remains constant. The temperature of the fluid remains constant. Right. So if you take all the steam out and then if there is only water, then the same pressure or the same temperature will not be maintained, right? So for this to be in this under the same line on the vapor dome, we there should be some steam and water existing.
Okay.
So as we take the steam out and add heat, some of the water is getting converted to steam, so that the temperature or the pressure is maintained and the pressure both are maintained.
Okay. Still answers are not matching. Your answer is also not coming as per the solution.
No, this U2 is 3711 megajoules, right?
Yeah.
But that is same as the solution, right? Or no?
No. Just 1 minute. I will give it to you. Solution is giving 3713.9.
Yeah, okay. Almost match. So now we need to find, we had from the steady flow energy equation, we can find Q and enthalpy that has gone out is to be found. Now NOHO is equal to 300 into Hg, enthalpy of the steam going out, that is 300 into Hg is, we have found out here, 2798.3. 2798.3. So this is This is 839,490. Okay, so yeah, this is 490 kilojoules or 839.5 megajoules. Now we had delta U is equal to U2 minus U1 is equal to Q minus MOHO. U2 is 3711 minus U1 is U1 is 3979 equal to Q minus MOHO is 839.5. 839.5. So Q is 3711 plus 839.5 minus 3979. this is 571.5 megajoules. So similarly we have so this is the heat that is added to maintain while we take out from the upper valve. And similarly the next problem is what if we take it from the lower valve, that is we take only water out of the system. So the amount of heat which must be transferred if 300 kg of fluid is allowed to escape slowly via the lower valve while the upper valve remains closed. So for this U1 is same, U2 will also not vary, because we have only taken the total mass and then found what would be the share at the second state. So U1 U2 are same, and now only MOHO will change, that will become 300 kg into H of the fluid at the liquid state. So this is 300 into, it was 908 point something, 908.5. This is 272,550 kilojoules or 272.5 megajoules. Now U2 minus U1 is equal to Q minus MOHO. We have Q is equal to U2 is 3711 minus 3979 plus MOHO, that is 272.5. So this comes to be comes to be 4.5 megajoules or 4500 kilojoules. Okay, anyway we have to round off to the nearest integer, so this can be rounded off to say 5 megajoules. Do you have any questions? I think this part is little tricky, like we tend to take only the steam out and then calculate later, but since we have to maintain the temperature to be in the same equilibrium, it has to be within this vapor dome, and we have to solve it differently.
There actually I made the mistake. So can you go to the slide again, how to calculate that final internal energy?
Yeah.
Because now proportions are changing na? After letting out steam 300 kg, the proportions of steam and mass is changing. What
Yes,
I have taken only mass of water.
Yeah. This slide you watched.
Backslide. One more. This one here. Up to M2 I was right.
Yeah. And then the ratio has to be
Hereafter I
calculated.
made the mistake. So M2 is Mg2 plus Mf2, where I have taken here M2 as only Mf2. That is the problem. So can you explain this step again? This one.
This
M2 is equal to Mg2 plus Mf2.
Yeah. So now we know for the boiler there is some level of steam and some level of water.
Yeah.
And we know total mass is known as some 3998 or 3998. And we know the total volume is also 10 meter cube. and for the steam phase we know Vg is known, Vf is known. So assuming Vg2 was the mass of the or the volume of the steam, I can write Vg2 divided by Vg, or the specific volume will give me the mass of the steam phase, and similarly the other volume is 10 minus Vg2, the liquid or the water volume is 10 minus Vg2, and then divided by the specific volume will give me the mass of the fluid.
Yeah.
So then we have this values, and now to solve this equation there are many ways, and I've taken like this, and then separated Vg2 in one place, and then I got 5.36.
Yes, got it, sir. Sir, one small query is there. That is from maybe assignment 4, I think. Just 1 minute I will take. I was not attended the lectures, but the query is in question they have asked the change in internal energy, like that questions are there. They have asked change. Now in question change is asked. I think in answer, my expectation is I have calculated answers right. Let's say minus 30 kilojoule. Okay. But as the change is asked, I have written there only 30. Okay, I have not written sign conventions. Because it is not asked as increase in internal energy or decrease in internal energy. Change can be positive or negative. You can't ask it with sign.
Yeah, I mean generally if you ask for change, then it is delta U is final minus initial, right? So then the sign should also be there. If it is asked for the increase or decrease, then you can directly say, like if it is, say if they ask for what is the decrease.
Yeah. But the literal meaning of change is what? It can be increase or decrease, na? So actually my answers were right, but only the thing is I have written magnitude there. And my suggestions to NPTEL team is there. Actually, I have given so many times this feedback. When you are giving the answers in rectangle, what is the problem in giving the options? Means there is no point. There is no point in giving the rectangle, because see, actually the questions are too tricky. They are not easy to solve, and just by luck, nobody give the right answer. Always there is a 25% probability.
Actually, even in that they have some tolerance of 5%. I think you would have seen in the when you see the answers, right? After the deadline, you will see the answers, and there is some 5-10% tolerance for the answer.
No, I agree. Range is no problem. Range is not the problem. Problem is what? Ki at least such kind of mistakes are avoided from the students. For example, minus 25. I know answer is 25, but in the answer, if out of 4 options, if I am seeing minus 25, I supposed to have clicked minus 25 only, na? I should not gone for 25 in that case. So I have given this suggestion lot of time, but no response from these peoples.
Okay.
So there you need, because you are asking feedback to us, and you are not taking that things into consideration. And we are not expecting from IIT people like this. Because it is all the thing is the learning process. No, but at least you should convey this message to that team. If you are giving the rectangle, means such kind of things should not happen. Na? Better to give options in that case, na? What is the problem in giving options? Means rectangle एक ही ब्लॉक देने से क्या वो ज़्यादा स्मार्ट होगा, वर्ड होगा, ऐसा नहीं है ना?
Sorry, English please. English.
No. I am not actually understanding the logic in giving to write the answer, entering in the boxes. What is the logic behind that?
I think Week8 also has a similar thing, no?
Huh?
So sometimes if the answer are like 2.5, 25, 2500, Some people can be smart enough to, without solving, they can directly put this magnitude, order of magnitude should be 25, so 25 is the right answer.
No, sir. For example, if now I am a teacher, I want to avoid the malpractice. What I will do, if the answer is 25.2, I will give 2.52. I will give 25.2. I will give 252 point something.
Yeah, still.
Like that I can do, na?
See, still looking at the order of magnitude without solving, I can tell, no? See, for some problem we had only 5 Kelvin increase in temperature or something like that, no? Yeah, here. So here if I give very off answers, I can directly say the answer should be within 6 and 60.
How we can say directly say 6 and 60?
Yeah, it should be within 6 and 60, right?
No. In this case, it's okay. But you can give 4 options in between 6 and 60, na?
Yeah.
That you can do, na? So how student can able to write just by hook or crook, just by luck? There is no chance at all. So I don't know why IIT people are trying to become smart by giving that a single box to enter the answer for the students. So I am actually having a strong resistance on it, sir. Otherwise, stop this work. There is no point in it.
Yeah, I hope you have already given the feedback in the.
Sir, in previous, I have done the course for thermodynamics also, laws of thermodynamics, where I was a topper. I have given IC engine and gas turbine, I was topper. I have given heat transfer course, I was topper. Three times I came topper.
That's nice.
I have given answers. Number of times I have given feedback, but they are not changing their attitude. So I am having a strong resistance on this. Otherwise कोई मतलब नहीं है सर इसका. आप learning दे रहे हो या आप smart बनने की कोशिश कर रहे हो? कोई पॉइंट नहीं बनता सर ऐसे. सारे कॉम्पिटिटिव एग्जाम निकाल के देखो, 4 ऑप्शन दिए जाते हैं. इफ यू आर स्मार्ट इनफ ना, डू गिव 4 ऑप्शंस व्हिच आर कंफ्यूजिंग. व्हाई यू आर गिविंग अ सिंगल बॉक्स?
So GATE also has such problems, no? You are against that also.
No. The system is like this. Why it is so? It is the MCQ pattern.
If you have a voting, no, many people will vote for this and some people like you could vote for that, so we don't know what is the majority.
No, I don't know. I am not understanding the logic. You can't defend such kind of things, sir. It's okay. ठीक है, आप मेरा मैसेज तो पहुंचा देना एटलीस्ट.
Yeah, I got your message.
जो भी आपके जो टीचर है, मींस जिन्होंने आपको ये अपॉइंट किया है, उनके पास मैसेज भेज दो कि
इंग्लिश प्लीज.
No. You just send the message to your who is actually the teacher or all IIT peoples ki some peoples are saying like this. What is the logic behind that? You can, if the teacher is smart enough, he can set 4 answers in such a way that students cannot answer it by luck.
Yeah, I will convey you, sure.
Okay, thank you, sir. Thank you.
So someone asked for the book, so these problems, as you may know, I have solved from the assignment, and some problems like this I take it from the Sengel and Boyles, and I also take some problems from Week8. Okay. Now next problem, we have air that enters a nozzle steadily at 2.21 kg per meter cube and 40 meter per second, and leaves at 0.762 kg per meter cube and 180 meter per second. If the inlet area of the nozzle is 90 centimeter square, determine the mass flow rate through the nozzle and the exit area of the nozzle. So we have row 1, so we have nozzle. This is state 1 and this is state 2. It enters at 2.21 kilogram per, so alright, row 1 V1 and some mass flow rate is constant. So here we have row 2 V2 velocity 2, and there is one area at the inlet and area at the outlet is different. So row 1 is 2.21 kilogram per meter cube and V1 is 40 meter per second, and leaves at row 2 of 0.762 kilogram per meter cube and V2 is 180 meter per second. Now if the inlet area of the nozzle is 90, so A1 is also given as 90 centimeter square. Yeah, sure, Dr. Anil Kumar, I will convey this.
Okay, thank you, sir. Thank you.
Yeah,
thank you, sir. Thanks a lot.
Now we have to find the mass flow rate through the nozzle. So m dot is row 1 A1 V1. So that is row 1 is 2.21 into area is 90 centimeter square. So convert to, yes, already left Anil Patil. 90 centimeter square, that is 90 to 10 power minus 4 meter square, and into V1 is velocity 1, that is 40. So this is 0.796 kilogram per second, and to find the exit area we have m dot is equal to row 2 A2 V2. So this is 0.762 into area 2 into velocity is 180, and m dot is the same, 0.796. So A2 is equal to 0.796 divided by 0.762 into 180. This is 5.803 into 10 power minus 3. Yes, this is in meter square, so convert to centimeter. We will have first 58.03 into 10 power minus 4 meter square. So this is approximately 58 centimeter square. Next problem, we have a hair dryer which is basically a duct of constant diameter in which few layers of electric resistors are placed. A fan pulls the air in and forces it through the resistors where it is heated. If the density of air is 1.2 kg per meter cube at the inlet and 1.05 kg per meter cube at the exit, determine the percentage increase in the velocity of the air as it flows through. So we know because of the steady state we can have m dot as row 1 A1 V1, that is equal to, so this is say at inlet 1 and this is at outlet 2. We have row 2 A2 V2. The diameter of the duct is constant, so A1 is equal to A2. We can neglect this term. Then we will be left with row 1 row 1 V1 equal to row 2 V2. Now writing V2 by V1, we have row 1 by row 2, that is 1.2 by 1.05. This is 1.142, and so now to find the percentage increase in volume, we will have V2 minus V1 by V1 into 100. So this is the percentage increase in volume, increase in the velocity. This is V2 by V1 minus 1 into 100, right? So then we know it is 14.2%. Substitute in V2 by V1 value, then you will get this. Do you have any questions? In the next problem, we have a desktop computer which is cooled by a fan whose flow rate is 0.34 meter cube per minute. Determine the mass flow rate of air through the fan at an elevation of 3400 meters where the air density is 0.7 kilogram per meter cube. Also, if the average velocity of air is not to exceed 110 meter per minute, determine the diameter of the casing of the fan. So rho is 0.7 kilogram per meter cube and volume flow rate is 0.34 meter cube per minute, and velocity is given. Velocity is 110 meter per minute. We have to find the mass flow rate and the diameter. So for mass flow rate, m dot is rho into volume flow rate, that is 0.7 into 0.34. So we can calculate the mass flow rate. That is 0.238 kilogram per minute, and for the diameter we can have m dot is equal to rho av, or velocity mentioned by small v. For rho we have m dot is known, that is 0.238, and rho is 0.7. area is what we need to find, and velocity is 110. So here both the sides I have per minute, so it is I need not convert to per second this time. And here now area is 0.238 by 0.7 into 110. This is, yeah, can you find area? Yes, this is 3.091 into 10 power minus 3 meters square. So area, it is given as a circular, so we need to find the diameter. So it means the cross section is a circle, so that is pi by 4 d square is the area, is equal to 3.091 into 10 power minus 3. So d is 4 into 3.091 into 10 power minus 3 by pi under the root. So this is 6.27 centimeters here. The next problem, we have the minimum fresh air requirement for a residential building is specified to be 0.35 air change per hour, that is 35% of the entire air contained in a residence should be replaced by fresh outdoor air every hour. If the ventilation requirement of a 2.7 meter high 200 meter square residence is to be met entirely by a fan, determine the flow capacity in liter per minute of the fan that needs to be installed. Also determine the diameter if the duct if the air velocity is not to exceed 6 meters square. So we can find the volume of the total room. So that is 2.7 into 200, that will be 540 meters cube, and 35% of this volume has to be replaced every hour. So we can find the volume flow rate as the 35% is 0.35 into 540 meter cube per hour. Just can find this. This is 189 meter cube per hour. Now we want in liter per minute. We know 1 meter cube is 1000 liters. So V dot is equal to 189 meter cube per hour can be written as 189 into 1000 liters by 60 minutes. So this is 189 into 1000 by 60 liters per minute. So this is 3150 liters per minute. Now we need to find the diameter of the duct. Now the velocity is given as 6 meter per second. So for a row of density is not given. Okay, that is not. So V dot is area into velocity, and area is pi by 4 d square. So V dot is equal to pi by 4 d square into velocity, and V dot is we know we can have it in this 189. This is in meter cube per hour. To convert to per second, we have to divide by 3600. So then it will become meter cube per second. Now we have pi by 4 d square into velocity. It should not exceed 6, so we have 6 here. Then diameter is 4 into 189 by 3600 into 1 by 6 pi. This is 0.1055 meter. Yes. Do you have any questions? Anil Patil, I think I'm seeing you after a long time, or you are, this is the first class you are attending. You can unmute and respond. First time, okay. So you are doing this course for to credit for your university, or you are just doing it separately? Oh, emitter. Okay. Which university you are from? Pune SPP. Okay. Okay. So, do you find this course very useful, interesting, or you are just seeing all the known concepts only? Are you learning something new? NPTEL star. What does it mean? fine. Okay, a house is maintained at 1 atmosphere and 24 degrees Celsius and a warm fluid dynamics and okay, fine. So a house is maintained at 1 atmosphere and 24 degrees Celsius. And warm air inside a house is forced to leave the house at a rate of 150 meter cube per hour. As a result of outdoor air at 5 degrees Celsius infiltrating into the house through the cracks. Determine the rate of net energy loss of the house due to mass transfer. So there is some control volume, which is the house. There is some air going out, and then because of some air coming in, the temperature inside is maintained at 24 degrees Celsius by adding heat to the system. And the air that goes out is so it goes out at 150 meter cube per hour, and the temperature will be 24 degrees Celsius because it is coming out of the room. And the air outside air is at 5 degrees Celsius, so whatever is entering inside will be at 5 degrees Celsius. Now from steady flow energy equation, we know Q is m into m naught, m in h in minus m naught h naught, or I think it is other way. So we can write change in internal energy is equal to Q plus m in h in minus m naught h naught. Here you can say internal energy there is no change in internal energy because it is maintained at 24 degrees Celsius, and Q can be found out by m naught h naught minus m in h in. Here the you can at steady state the mass will be the same, so it will be m dot into h naught minus h in. Now we need to find the mass flow rate. So find the mass flow rate, we need rho. So rho we can find from PV equal to RT equation. So here PV is equal to RT, where R is a specific volume. To have it as rho, we will have P by rho equal to RT. So rho is equal to P by RT. So rho is P is 1.01325 into 10 power 5 divided by R is 287, and temperature that is leaving is 24 degrees Celsius, that is 297 Kelvin. Yeah, that is 297. So can you calculate the value of the density? Yeah, this is 1.188 kilogram per meter cube. Now we can calculate m dot, that is rho into volumetric flow rate, that is 1.188 into 150. That is 178.2 kilogram per hour. To calculate Q, we have m dot into change in enthalpy. So now m dot is 178.2. So this is in kg per hour. So to convert to kilogram per second, we need to divide by 3600. And for the enthalpy in and out, we can have Cp into delta T. So this can be written as m dot into Cp, temperature outlet temperature going out minus temperature coming in. So Cp is 1005 into temperature that is going out is 24 minus temperature coming in is 5. So this we can calculate the value of Q. Yeah, this is 945.77 watts or 0.945 kilowatt. The next problem, air flows steadily in a pipe at 300 kilopascal, 77 degrees Celsius and 25 meter per second at a rate of 18 kilogram per minute. Determine the diameter of the pipe, rate of flow energy, rate of energy transport by mass, and also determine the error involved in part C if kinetic energy is neglected. So the pressure is 300 kilopascal, temperature is 77 degrees Celsius. To convert to Kelvin scale, we have 350 Kelvin. Velocity is 25 meter per second and mass flow rate is 18 kg per minute. Now we can find the diameter of the pipe. So to find the diameter, we need to have the value of density. So rho is P by RT, and P is 300 kilopascal, 300 into 10 power 3 pascals, divided by R is 287, into temperature is 350. So we can calculate the value of rho. Yeah, 2.986 kilogram per meter cube. Now we can calculate m dot is rho into A into V, or velocity. Rho is given as m dot is given as 18 kilogram per minute, so it is 80 by 60 in kilogram per second. Rho is 2.986 kilogram per meter cube, and for area we have pi by 4 d square, and velocity is 25. So d is 18 into 4 by 60 into 1 by 2.986 pi into 25. Can you calculate the diameter? Zero point zero seven one five meters. So this is 7.15 centimeter. So now we have calculated diameter. Now we need to find the rate of flow energy. So rate of flow energy is m dot h. So WF is, I consider WF as rate of flow energy, or W dot F. M dot is 18 by 60. For flow energy it is Cp into T. This is Cp into temperature. Cp, since it is known that it is air, we have Cp as 1005 joule per kg Kelvin, and temperature is 350 Kelvin. So we can find the rate of flow energy. It is 105.525 joules per second. So that is watts. So we can have 105.5 kilowatts. Now rate of now the rate of energy transport by mass is total energy, it is W dot is m dot h plus m dot v square by 2. Now this is known as 105,525 plus here for the kinetic energy we have 18 by 60 into v square by 2, that is 25 square by 2. Can you calculate W naught? So this is 105,618.75 watts, that is 105.62 kilowatt. Now the next part is to find the error involved in part C if kinetic energy is neglected. So percentage error is equal to W dot minus W dot flow energy divided by W dot. So that is 105.62 minus 105.5 divided by 105.62 into 100%. Can you calculate the percentage error? This is 0.1136%. So the percentage is very low. When we neglect the kinetic energy term to calculate the flow energy or the total energy. Now air enters an adiabatic nozzle steadily at 300 kilopascal, 200 degrees Celsius and 30 meter per second and leaves at 100 kilopascal and 180 meter per second. The inlet area of the nozzle is 80 centimeter square. Determine the mass flow rate through the nozzle, the exit temperature of the air, the exit area of the nozzle. So to find the mass flow rate, we want rho into A into V. At the inlet we know pressure and temperature and velocity area, so only rho has to be found out. So rho is P by RT. This is 300 kilopascal, that is 300 into 10 power 3 divided by R is 287 into temperature is 200 degrees Celsius, so that is 473 Kelvin. Calculate the density. .21 kilogram per meter cube. So now m dot is 2.21 into area is 80 centimeter square, that is 80 into 10 power minus 4 to write it in meter square, and velocity is 30. Can you calculate the mass flow rate? .528 kilogram per second. Now the second is to find the exit temperature of the air. So we know m dot will be same at the steady state at the outlet as well. So m dot is equal to rho to A to V2. and rho 2 we know that it is P by RT, so m dot is also known. M dot is 0.528 into rho 2 is sorry, this is equal to P by RT. So P is 100 kilopascal, 100 into 10 power 3 divided by R into T. R is 287, temperature is not known, and area is also not known. But V2 is known as 180 meter per second. Any idea how we can solve this? This is only by having the continuity equation. Now if you balance the energy, that is H1, that is, so this is inlet and this is outlet 2, H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Now we know both the velocities, and H is known as Cp into T. So with this we can calculate the T2. We have this as Cp into T1 plus V1 square by 2 is equal to Cp T2 plus V2 square by 2. T2 is, or now T2 is equal to T1. I can divide everything by Cp. Then I will have plus V1 square minus V2 square by 2Cp. This is T1 is 200 degrees Celsius, that is 473 Kelvin, or I can have it as 200 degrees Celsius as well, because finally I will get to T2 in degrees Celsius. And V1 square minus V2 square. So for V1 we have 30 square minus V2 square is 180 square by 2 into Cp is 1005. So this way I can calculate T2. Yeah, 184.33 degrees Celsius. Now T2 is 184 degrees Celsius, and in terms of Kelvin it is 457 Kelvin. Yeah. So from this equation I know it is A2 is 0.528 into 287 into 457 divided by 100 into 10 power 3 into 80. Can you find the value of A2? This is 3.847 into 10 power minus 3 meter square, or 38.5 centimeter square. The next problem, we have air that flows steadily at a rate of 0.5 kilogram per second through an air compressor entering at 7 meter per second velocity, 100 kilopascal and 0.95 meter cube per kilogram volume, and leaving at 5 meter per second, 700 kilopascal and 0.19 meter cube per kg. The internal energy of the air leaving is 90 kilojoule per kg, greater than that of the air entering. Cooling water in the compressor jackets absorb heat from the air at a rate of 58 kilowatt. Compute the rate of shaft work input to the air in kilowatt and find the ratio of the inlet pipe diameter to the outlet pipe diameter. So we have a compressor that can be assumed as a control volume, and air is going inside and air leaves at some state. So while entering, it has throughout the m dot is same, that is 0.5 kilogram per second, and while entering the velocity is 7 meter per second, 100 kilopascal, and the volume is 0.95 meter cube per kg. While leaving, the velocity is 5 meter per second, 700 kilopascal and 0.19 meter cube per kg. The internal energy change is that is between the inlet and the outlet is 90 kilojoules per kg, and some heat is some work is done on the system and some heat is lost outside through the cooling water, and that is 58 kilowatt. So using all this, applying in the steady flow energy equation, we can get the values. Since the change in internal energy is given, delta U is 90 kilojoule per kg. We can say this is it is per kg, so we will have only CV into delta T. So 90 into 10 power 90 is equal to 0.718 delta T. So delta T is 90 by 0.718. That is 125.34 Kelvin or degree Celsius is the change in temperature. So writing the steady flow energy equation, we will have change in internal energy of the control volume. So this should not be confused with the change in internal energy of the air coming in and going out. Change in internal energy of the control volume is heat that is given in minus work that is extracted out. So generally we assume positive heat transfer means heat is transferred to the system, and positive work is work is done by the system on the surrounding. And then we have m inlet with an enthalpy Hi minus m outlet with an enthalpy H0. Here the change in internal energy of the system is 0 because it is at a steady flow. The internal energy of the compressor as such is 0. So if you take this as the control volume, internally there is no change in there is no change in internal energy of the compressor, but the energy possessed by the air coming in and going out is changing. So that is here M in and M inlet and M outlet is same, and we can, so M inlet minus M H is M into M dot into H inlet minus H outlet. So this is M dot into delta H, and M dot is H, delta H we know it is delta U plus PV. We have H equal to U plus PV, so deltas or dH is equal to du plus pdV plus pdP. Alright, so this is M dot, so this is delta of this one, so this is delta U plus delta P into V. We cannot, I think it's better we assume it as an ideal gas and then proceed. So this is M dot into Cp into delta T. So delta T is known, and we need to find M dot as well. So how can we find M dot? Using the inlet conditions. So actually we are also having, in addition to the enthalpy, we also have M inlet, H inlet plus V inlet square by 2 minus M outlet, H outlet plus V outlet square by 2. So here we can find M dot. So for M dot we need to find density. Density is given by P by RT, or we already know that the specific volume is 0.95. So we know volume 1 is 0.95 meter cube per kilogram. Sorry, M dot is given, it's 0.5. M dot is 0.5 into Cp is 1005 into delta T is what we have calculated as 125.34. So this is 125.34. So M dot into delta H can be calculated. This is 62983.35. This is in joules, because 1005 was in joules, we will get the result in joules. Now similarly we have change in kinetic energy. Change in kinetic energy is M dot into Vi square by 2 minus Vo square by 2. So that is 0.5 into V inlet square is inlet is 7 and outlet is 5. So we have 7 square by 2 minus 5 square by 2. So what is the change in kinetic energy? So that is 6. It is 6 joules. 6 joules. So this is almost negligible when compared to the total change in enthalpy. now we writing this steady flow energy equation. We have Q minus W is equal to m into m dot into delta H. So here Q is given as minus 58, right? Yeah, 58, which is minus 58 minus W is equal to m dot into delta H is 983.35. So this is joules per second because we had m dot, and here now we have in watts. So to convert into kilowatts we have to divide by 1000. I would write this as 62.98 kilowatt. This is 62.98. So now work transfer is equal to 62.98 minus 58. Yeah, minus 62. Yeah, so it is minus 120.98 watts. So that means sorry, this is in kilowatts. So around 121 kilowatt of work is transferred for compressing, and that will be the shaft work. So this is for shaft work, and we have to find the ratio of the inlet pipe diameter to the outlet diameter. For this we know m dot is equal to rho 1 A1 V1 is equal to rho 2 A2 V2. Rho 1 is specific volume is 0.95, so rho is 1 by 0.95, so this is 1 by 0.95 into area is pi by 4 d1 square into velocity is 7 at the inlet. 7 is equal to rho 2 is 1 by 0.19 into area 2 is pi by 4 d2 square into into velocity is pi 5. So we have d1 by, so we want to find the ratio of inlet pipe diameter to outlet. So d1 by d2 is, we have 0.95 by 0.19, so pi by 4 will get cancelled, and then we will have into 5 by 7 under it is 1.889, so almost 1.9 plus d1 by d2. Do you have any questions? It's time now, so I will close the session. Thank you for joining. We'll see you in the next class.